Now let's take a quick look at strategies which seek to approximate or infer deep network structure using more traditional machine learning approaches, specifically manifold learning of latent codes and the use of simple intuitive methods such as random forest and linear regression to act as surrogates and approximate the inferences of deep networks local to specific examples from the dataset. So hopefully all of you have come across approaches for latent factor or manifold learning during your earlier courses on machine learning. These work by seeking to project data to a lower dimensional space which nevertheless captures key properties of the dataset. For example, the variance structure when we're using PCA, or the distribution of local neighbourhoods for manifold learning. Where in the specific case of manifold learning, the assumption is that data points lie on a low-dimensional, non-linear manifold embedded in a high-dimensional space. For example here, the famous Swiss roll example, which is a 2D plane wrapped up into 3 dimensions. In this space, Euclidean distances between points are not good representations of the underlying structure. Instead, they create shortcuts between points which are, in reality, quite far apart on the original manifold. Indeed, the mathematical definition of a manifold is a space for which Euclidean geometry holds only locally. There are a number of different manifold learning techniques which differ primarily in the way in which they infer these geodesic distances between points so as to unroll the manifold into, say, a 2D representation. But, as all of these simply expect an input of a matrix of feature vectors where these feature vectors reflect some low-dimensional summary of our data, then it means that we can use these to investigate the latent space of our deep models. Where by latent space I specifically mean either the last linear layer of a classifier network, or the bottleneck representation of an autoencoder, or indeed a generative model. So this latent space represents the point at which our deep network has most compressed the feature representation of our image. And in principle, it should contain all information required to categorize the object. So naturally, we should expect that when we look at the similarity or distances between latent codes for different examples, we should be able to see that these cluster intergroups are representative of different objects. And while we could use popular manifold learning techniques such as Laplacian eigenmaps, the most commonly used manifold learning technique used for investigation of deep networks is called TSNE. This is an algorithm developed by Van der Marten and Hinton in 2009, which assumes that geodesics between distant points may be inferred through random walks on local neighbourhood graphs, similarly therefore to Laplacian or diffusion map embeddings. TSNE, however, differs in that its definition of these local neighbourhoods is tuned based on an estimation of local probability distributions, which are designed to allow for different cluster densities in different parts of the latent space. It is suggested that this makes it better at simultaneously capturing local and global relationships between points, and it's regularly been shown to be very powerful for modelling deep latent spaces, provided one is careful with the parameterization. The way it works is by learning embedding coordinates y, which are optimized to preserve the local probability density relationships in the high dimensional space, such that in the 2D or 3D embedding that is created, points which were close on the assumed highly nonlinear manifold of the latent code will remain close in this embedding space. This similarity is estimated from a normalized conditional Gaussian distribution function, such that the probability that some point j would pick I as one of its neighbours is given by the following expression, where a point cannot pick itself as a neighbour, and the variance term sigma I is tuned for each point in order to fix the number of neighbours considered by each point as constant irrespective of the local point density. This is achieved by setting a perplexity parameter, where during optimization, TSNE performs a search for the value of sigma that produces a probability distribution with perplexity equal to this target value. This perplexity itself is estimated from the Shannon entropy. So it essentially just reduces to tuning the number of neighbours considered within the local probability distribution for each point, where typical values for this perplexity tend to range between 5 and 50. Just a small word of warning that in some cases changing this perplexity value can have quite a big impact on the way that the final embedding looks, so it pays to be cautious when interpreting the results. For more details on this, consider reading the following article. Then, once the conditional probabilities are inferred in the original space, embedding coordinates are estimated by optimization so as to preserve the Kullback-Leibler divergence between these two probability distributions. Where first one needs to deal with the fact that the conditional probability of j given I and I given j will not be equal by default, so this distribution needs first to be symmetrized by averaging them. The positions in the map space yi and yj are then inferred through enforcing that the distances between points in the learnt map space should follow a student's t distribution, where this is essentially a long-tailed Gaussian, with the constraint that this should approximate as closely as possible the conditional probability distributions in the high-dimensional space. In other words, the yi are estimated by optimizing the Kullback-Leibler divergence between Pij and Qij using gradient descent. And finally, for this section, we'll briefly review an example of what is known as a surrogate model, where the idea behind these is to use an inherently interpretable method such as random forest, or anything for which the mapping from explanations to features is explicitly clear, in order to approximate the predictions of a black box learning model within a region local to some specific example. For example, take this visualization, where we are imagining some deep model which is learning some highly nonlinear function indicated by the blue-red boundary. Let's say we're interested in what's driving the predictions for some specific example indicated by the big red cross. The idea behind LINE, which is the local interpretable model agnostic explanations, is to create some new data set of perturbed examples of X, for example, by applying augmentations to the data. We then obtain the predictions from the black box model for these, and then fit a much simpler intuitive model to these predictions. For example, we might use linear regression with Lasso or a random forest, where the features which these are built from will be simple hand-engineered ones. For example, just average image intensities within small regions of the image. The objective of this simple classifier is then to minimize the mean square error between the predictions of the black box model and the interpretable one, whilst keeping this complexity as low as possible, so reducing as far as possible the number of features that are required to make the prediction. This final model will be approximate and only locally accurate, so you're only making a prediction within some local part of the domain. But it gives us more information than just what the model is looking at, going further to try and figure out how different features are combining together to make this prediction, and in what order of importance. And when it comes to clinical applications, this type of information is really important. If we want to go beyond just identifying what in the image is important to a prediction, but instead start to build mechanistic models of disease to support development of new treatments or prognostic models. So, in summary, the latent space of a deep network indicates the point at which information has been most compressed, but should nevertheless contain all the information required to make predictions, and thus it should encode the similarities between data points. This means that we can visualize relationships between examples using manifold learning techniques such as TSNE applied to this latent space. On the other hand, surrogate models are instead working to try and understand how deep networks are making their decisions by building approximations local to some specific data point using inherently interpretable methods such as linear regression or random forests. The goal of this is to approximate not just the features which are important, but also how they combine to make a final decision.